Welcome to class. Come on in. Hello, come on in. We got a few minutes before class starts. Feel free to ask me questions if you have any. 81? Anyone? Oh,
I was actually away from my computer. Did you ask something?
I just offered to answer any questions people might have. I've been posting some recent videos showing more examples of Gauss's law, which is hopefully you've seen now from the chapter on capacitance, how Gauss's law is used to calculate capacitance. So I did post some more videos on my YouTube channel. Hopefully y'all have subscribed to that. Then you'll just get notifications. If you haven't, then just keep an eye on it. I think I did make one link for one of them anyways in your Canvas course. I did a nasty one today. Made it up and it had a inner cylinder and then an outer cylindrical shell that had a finite thickness and had different charges per unit volume, and I just sort of made it as ugly as I could and as hard as I could so I could make sure you guys knew what was going on.
So, for do we have a test coming up here shortly, don't we?
Yeah, I think I already put it up. In fact, let me double check with that. I sent out a text message, announcement to everyone today, just letting them know. I'm probably going to put up practice test 2 as well, so we can get on board with that. So if we look in the section called practice tests, I now have practice 1 test and practice 2 test open. And February 8th, practice 2 test 1 disappears, which means February 8th should be the day that test 1 is due. And that is in fact the case. So test 1 on chapters 21 and 22 is due by 11:59 p.m. on February 8th.
So I actually came from Virginia Peninsula Community Colleges, and I actually live in Chesapeake now. So I came over here, and
gotcha.
My first physics class teacher was awful.
Sorry to hear that.
And like he would post practice tests, and then like everything on the practice test had absolutely nothing to do with the actual test itself. So
yeah, sometimes that's hard not to do. I mean, sometimes there's a way you can do that by accident. I basically make my whole bank available more or less. I reserve the right to like make 20% of the points come from something new, but so far I haven't needed to. So literally, if you were to take my practice test an infinite number of times, you will have seen every question that's going to be on my tests. That being said, it's not a small number of questions. So it's not like you could just do it 10 times and be done with it.
It was the worst part is like he would teach something and use a certain formula, and then from the same chapter he would put a question up there and then a completely different formula I had never seen my entire time would be used, and I was like, how did we get here?
Yeah, physics is hard to teach. I don't necessarily, I mean, I think I try to do a good job, but I'm not sure I do that good a job, even though I've been working on it for 20 years. I know sometimes I get a single problem explained pretty well to a student, and that makes me feel like I had a good moment. But generally speaking, I very rarely feel like I do that good of a job.
You're doing better than him, but
well, thank you.
He nothing against you, but he set the bar low for every teacher I've had.
Yeah.
I'm pretty sure I'm a grown man, and me and him almost stepped outside the classroom a couple times.
Yeah, I had a fellow grad student was sitting outside the hall one day watching him teach. It This was oh, I shouldn't say where it's at. I'll just leave it as one of my grad schools I attended, and he was doing what we call recitation at nice, expensive Ivy League schools. Everybody's either wealthy enough or paid for enough where they can take a 6-hour class and then do 3 hours for free, which is what recitation is. Every time I've offered it at a community college, I literally get one student who was already making an A showing up. So we don't do it, but that's how a lot of how they succeed. So I have 3 hours of lecture from their instructor who more or less just covers the concepts, and then they'll have 3 hours of lecture by their grad students who takes questions on problems. And one of my fellow grad students was doing that for one of the instructors. And the student said, I don't understand how you got from here to here. He said, what, you don't believe me? And like walked off.
That's almost word for word. This dude was like, one of the students asked him a question, was like, hey, can we do it this way? Or like, was like, hey, can you explain it a different way? And he's like, no, I'm not going to do it your way just because you're asking me to. We're going to do it my way. I'm like, dude, me and you about to have it right now.
Was his first name Michael? And did he look like he might have been from a foreign country?
No. He was, man, I'd be honest with you, I don't even remember his name.
A friend that did that is actually, he was adopted from like Vietnam. His parents did a really nice thing and adopted a child unseen from Vietnam. And he actually ended up going to a local school and everything. For his undergraduate degree, and then Chapel Hill and another school for his graduate degree. So I don't know where he is now, but I would not be surprised to find him back in Virginia. He went to Mary Washington, I think was the school. It was one of those schools in that area. So we got more people in. Anybody have any questions? It's about time to start. I've got some problems slated. I was just telling James and the other people that are in here, I have been posting more videos on my YouTube channel. I'm trying to do more where it's just like a problem as opposed to, I always post my lectures. So again, if you guys are having any issues with material that you missed, you can always find the exact same lecture from a year ago or last semester or something like that on there. But I'm also trying to make shorter versions so that it's not a whole hour and 40 minutes for you to figure out something. So like today I think I did 2 more, and then I did like 7 more in the last few days. Sometimes they're just hard. For instance, the conducting sphere's electric field determined using Gauss's law. I had to explain that in detail. So sure enough, even though it was just a sphere, it took me 38 minutes and 40 seconds. A density of water conversion took me 33 minutes, but I did a lot of extra stuff with that. But some of them are 5 minutes and 58 seconds or 10 minutes and 50 seconds. I was trying to see the time on the one I just posted, which is called a tough cylindrical Gauss's law problem. Oh yeah, that ended up taking 45 minutes. So I apologize for that, but sometimes, hard physics problems take a good deal of time. I don't think it's supposed to take as long as it did for me when I was an undergraduate, but I remember my first junior, senior level class that I got in, we had a homework set. It was like 18 problems, which was, I thought that was a fairly reasonable number of problems, but I realized later that it wasn't. And in fact, one problem I think I spent 7 hours on, and I was like, man, I don't know, I shouldn't be a physics major or something, because that's just a lot of work. And then I got in the day it was due, and I turned it in, and I turned in like this big stack of paper. It was a good 45 pages of handwritten problems solved. And then I looked, and everybody else turned in like 1 or 2 pages. And the instructor called me after and said, your work looks great. In fact, I was able to use it as the key, and that made me feel a little bit better. But evidently that was an abnormal thing. He had hoped that's what students would be, but in general, they weren't. So sometimes it's just It's just one of those things where it makes you feel like you're not ready. So don't get discouraged. I was pretty confident I was not ready for physics, but I quickly discovered when my teacher told me, "No, you're the only one that did okay." That was the case. And then when I got to grad school, it was just, even worse. So yeah, Christina, go ahead. Or sorry about the Hun crack. That's just something I do because I'm from the South, I guess. I apologize. But Christina, yes.
Yeah, no, the test is due on the 8th, right?
Yes, you have. I mean, it's available now, so you can do it as anytime you want, and you get up to 3 attempts. But yeah, it's got to be done by the 8th.
Sorry. When I looked earlier, it was not published yet. Like the practice tests are published, but not the actual tests.
Let me double check and make sure. Oh, I see. Yeah, you're exactly right. I must have accidentally hit the online test button. There's a button, which I don't know if you guys can see it or not, at the top of each module. And if you just slide over it and happen to be pushing a little hard on your trackpad, it'll just turn it from published to unpublished. So yeah, thank you for letting me know in real time, because that would have cost us a little bit of time.
No worries. Oh, also thank you for the individual chapter practices.
You finding those helpful?
Yeah. Well, last semester you posted some at the end of the semester, and I was like, I wish I had these towards the beginning of the semester. So
yeah, I think they're a little more focused of a problem set, so you get a better feel for what the test is going to be like. So really, I mean, and that's why the homework assignments, in my estimation, are actually quite short. There's usually per chapter, I only assign 10, maybe at most 18 or 20 problems for homework that are actually physical problems to solve. So I'm completely cool with you doing that number of problems, and then hitting the chapter practice all you want, because that's definitely a much better scenario. In general, I think any instructor, at least in chemistry, physics, math, engineering, at least in regards to statics, dynamics, and strength of materials, structures, geoengineering, foundations, stuff like that, all those branches, I guarantee you, anything that makes you do more problems, they'll be happy with. So yes, the test is available now. Y'all can take it, but thanks to Christina, she let me know that I had not published it. Now I got to check the other class too to make sure that's working. Anybody else have any questions or comments or anything? We still got people coming in. All right. Well, I guess I'll go ahead and get started then. So we're working still on capacitors, and in fact, I'm probably going to use one more day on capacitors, because there's a lot of stuff in it. And one thing that's really critical to this course is one of my capstone problems, and the classic capstone problem is worded like this. So everybody, please pay attention to just this part at least. I would like you to, one, use Coulomb's law, or hopefully for your sake, Gauss's law, to compute the electric field of some kind of charge distribution. Okay. Specifically, if we're lucky enough that the charge distribution is planar symmetric, meaning it's like an infinitely large plane, or cylindrically symmetric, which means it's an infinitely long wire of charge, are spherically symmetric, which means it's like a sphere with some amount of charge either throughout it, on it, in it, whatever, then those symmetries normally allow you to use Gauss's law to compute the electric field due to that charge distribution. That would be like step one of this problem that I'm referring to. Step two, or maybe even part B of the problem, would be, okay, use V, the change in voltage, which is V final minus V initial, which is defined to be the negative integral of E dot dl, E a vector and dl a vector, hence the dot product, a path / line integral, to compute the voltage difference between the two parts of the charge distribution. So in this case, it'd be like two parallel infinitely large planes, or at least two parallel planes that are so close together that their size is way bigger than that closeness. Or it would be a cylinder inside of a cylinder is another scenario. Or it could be a sphere inside of a sphere. Or in fact, as you'll see, one of the examples in your book did, it could be a cylinder next to a cylinder. Okay. Each one of those scenarios allows you to calculate a voltage from one of those charges to the other. And basically the deal is it's essentially always one has a positive charge and the other one has exactly the opposite negative charge. That would be part B, using that line integral to compute the voltage difference between the two. And then part C would be now calculate the capacitance of that, given that C is equal to the charge divided by the voltage. And when you do that process, which you can see a lot of on my YouTube videos where I'm doing whole lectures, basically I go through that whole process and I compute the formula for a charge distribution that's being treated like a capacitance. So you'll see, for instance, the video I posted today is called a tough cylindrical Gauss's law problem. That problem is immediately just ready to say, okay, Mr. Younger wants to know what the capacitance is of this distribution, which was basically a coaxial cable. It had an inner cylinder of radius r sub a, outer cylindrical shell of inner radius r sub b, and outer radius r sub c. And I would typically just ask you to calculate the voltage between, RA and RB, and then use that to calculate the capacitance. That's a very real scenario, but that's like a capstone problem for a huge swath of the material we cover, because it really covers chapters 21, 22, 23, and 24 in some sense. Not only that, later in the semester, we're going to run into an exactly parallel paradigm where we can either use the law of Biot-Savart, which you're not going to believe how complicated that looks when you see it. It's an integral. It's got, instead of a dot product inside of it, it's got a cross product inside of it. It's got, it just looks horrible, but it's really a cool formula. So that's the law of Biot-Savart. So unlike the one I just told you, where you could use Coulomb's law or Gauss's law, in this case, you're going to either use the law of Biot-Savart, which is the complicated one, or Ampere's law to compute a magnetic field for a given distribution. And the distribution essentially has to be a cylindrical wire, long and thin perhaps, or a solenoid, which is a wire like you used to make an electromagnet by wrapping around a nail, or a solenoid that's wrapped around on itself in a circle, which we call a toroid. With those beautiful symmetries, you can readily calculate the magnetic fields for them. And then you can use something called the flux, which y'all ran into flux before, but in this case, it's going to be called the magnetic flux. And if you divide that magnetic flux by the current, you will get something called the inductance, which we measure in henries. So that process is exactly similar to the process of going from Gauss's / Coulomb's law to capacitance. But in this case, you're going to go from Biot-Savart / Ampere's law to inductance. L is the symbol we use for that. So those are two really big capstone problems. So whenever you see me doing anything like that, whether it be in any of the videos online, that's what you want to pay attention to. Those are the problems that often, like on a midterm or a final, I'll make just that one problem. You'll be reading it and it says, warning, immediately after this test, you need to take a photograph of the work you did, showing all your steps, make it nice and neat, and then email it to me within 15 minutes of completing your test or something like that. That most often happens with one of those type problems where you start off with Coulomb's or Gauss's law and end up with calculating a capacitance, or where you start with Biot-Savart or Ampere's law and end up calculating an inductance. So just be advised about that. Any questions on all that gobbledygook that I just said? That's technically the official word, by the way, of all that stuff I just said. So we're all good. Okay, so what I will tell you is the behavior of capacitors is a neat little thing, and I'm going to, since I didn't do it in lecture last time, but I did do it in my other classes lecture, I'm going to give you a rather quick derivation. and hopefully some understanding of how capacitors behave. In their simplest sense, a capacitor can be thought of as two plates, one of which is charged a positive amount, the other which is charged a negative amount, and their closeness to each other is really, really infinitesimal compared to the distance from any spot inside to the edge, just about. And hopefully, since you guys have now had the electric field mapping lab, you've actually seen when someone actually takes two parallel plates that the equal potential lines are parallel to the parallel plates. Therefore, the electric field is essentially horizontal lines this way, and uniform, obviously pointing from the positive side, the high voltage positive side to the low voltage negative side. And you even saw that near the edges, there might have been a little diverging of the electric field. In other words, the electric field looked like perfectly horizontal lines, but once you got near the edge, it might leave a plate, go out here, and then come back and hit the plate perpendicular to the surface, because metals are equal potential surfaces, and therefore it's an equal potential line, and therefore the electric field has to be perpendicular to an equal potential line. So y'all have seen that, hopefully. What I'm going to do is I'm going to allow you to imagine what's going to happen when I connect a battery via wires to a capacitance, and then to a capacitance next to it in what we call parallel. And then I'll do the same thing for series. What I want you to understand is, generally speaking, when you're working with circuits, the wires in the circuit almost always have negligible resistance. It's not true that they have negligible, that they have zero resistance, but it's pretty darn close. So for instance, if you were to, let's say, take the COM end of your multimeter, which is properly set to DC volts, you know, the V with a little dash, 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 and then a flat line over top of it. If you take that black COM port and stick it on the negative side of a battery, okay, and then you stick the red part right at the positive side, if it's a AA or AAA battery, or a C battery, or a D battery, or even some other ones, it'll read like brand new, it'll read like 1.78, 1.75. What the nominal voltage is for that, is that's supposed to be good as long as it keeps up to 1.5 volts, no matter what current you put on it. So we'll just say it's a 1.5 volt source. Now, if I take that wire that runs from the positive nipple of a battery and it runs all the way around to, say, an edge of a capacitor, now I'll leave the COM on the negative side of the battery, and I take my red part of my voltage / multimeter and put it right next to that positive side of the capacitor. In principle, that's not going to be exactly 1.5 volts anymore, because the wire actually has some resistance. But what I'm trying to express to you is it would probably be like 1.4993. So it'd literally be like in a third or fourth decimal place before you could notice that it's not truly 1.5. Okay, so that's the way these things behave in terms of wires compared to resistors, which we haven't studied yet other than our Ohm's law lab, and capacitors, which we're getting ready to do now. So I am saying, and I almost sounded like I heard an M in the word I just said, I want to let you know that I'm saying capacitor, CAPACITOR. I apologize if I said capacitor, but I don't know where it came from either. All right, so let me start off. I'm going to share my screen with you because I'm so smart that I remembered it just before I started writing. I'm going to share my screen with you. It cracks me up every time I forget that. It doesn't take much to entertain my small little brain. Okay, so here we go. We got that, and okay. So what I am going to do is first let you imagine what happens when I take a battery, let's say a battery of V volts. Okay, now the symbol for battery is either that, or sometimes you might even see it's that, because really, to be honest with you, if you really wanted to make a battery, you could take like a prescription pill bottle and maybe take a penny and solder one edge of the penny to a wire, you know, a housed wire, and then run that wire from, well, lay the penny soldered side down in the pill bottle, and then run that wire outside of the pill bottle. Then backfill that pill bottle, say with lemonade or orange juice or just about anything other than distilled water. Distilled water would be probably the worst case scenario. It'd probably still work a little bit, but something with a little acidic or something with a little basic juice would be good. Then you put a little gauze, say, on top of the penny. And then you take a little zinc washer. That's that shiny looking silver material that they say is good for indoor and outdoor, but it's really not. It sucks real bad. But the main thing is any metal other than the copper that's plated with are ultimately, once the plating wears off, whatever metal's under it, which is probably zinc, to be honest with you. But still, just any dissimilar metal will work. You lay that metal on top of the gauze, and now you connect a battery or a a multimeter / voltmeter. You connect the one side, say the COM, to the penny, and the other side to the zinc on top, and you'll get a very small voltage on the order of 0.1, 0.2 volts. But if you put another gauze on top of that zinc washer, and then another penny on top of that, and then another gauze, and then another, you can actually add up that point. If it was 0.1 for just two different metals, if you stack that over and over and over again until you have 100 of those, then you'll have, in fact, 10.0 volts. And hence, that's why the symbol for a battery looks like a stack of stuff. And in fact, we've used that terminology ever since, where we call basically any power supply a pile. When Enrico Fermi did his first controlled nuclear reaction, that was called the nuclear pile. So anyways, that's what your battery is. And the long side that I've drawn here corresponds to the positive end of the battery, which for AA, AAA, C, and D batteries is the little positive nipple on the top. The negative side of the battery, that negative end, has a little bit of a dimple, and that's the negative end. But now we're going to run a wire which has little or no resistance up, and then it's going to go over to the left-hand side of a capacitor. And that capacitor is going to have a capacitance C1, and then that side of the wire is going to run back and come back to the battery. That's for just one capacitor. Now I'm going to put another capacitor, in fact, in parallel with that one. And connect it like that, and that's going to be C2, okay? Now, what's going to happen is this battery is going to sense, hey, I've got a conductive path leaving from the nipple of my battery, the positive aspect of the battery, which has a high electric potential as well as a high potential energy for positive charges. Therefore, the positive charges are going to leave the battery. And let's say the positive charge that leaves the battery is big Q. Now, what's going to happen is right here, big Q is going to have a choice. How much of it goes to C2 and how much of it goes to C1? In fact, what's going to happen is I'm going to call the amount of charge that goes to this one Q1, and the amount of charge that goes to this one Q2. And by conservation of charge, you know that Q has got to be equal to Q1 plus Q2. Does that make sense to everyone? So
Yes.
This is the part, for instance, thanks, Christina. This is the part, for instance, where I advise you guys to make sure you read the stuff where they told about what happens when you charge something and connect it to a metal in that chapter 21. This wouldn't be a bad time for you to go back and read chapter 21. It might actually make a little more sense, at least the parts that they're talking about induction and polarization and charging and stuff like that. Because what you'd realize would happen is you're going to get a buildup of charges on this left-hand side of C1, and you're going to get a buildup of charges on the left side of C2 as well. And they're all going to be positive. And in an attempt to show that C1 and C2 are different, I put a different number of pluses on C1 than I did C2. Now that plus charge on the left side of C1 is going to compel the positive charges in the right hand side of that plate to run away, and that's going to make an equal amount of negative charge on the right plate. And the same thing's going to happen with C2. I'm going to have the same amount of negative charge on the right plate as I do on the left plate. So ultimately, what's going to happen is Q1 is going to enter this junction, and Q2 is going to enter this junction, so that the battery just gets a final charge Q coming back into it. But at that point, the battery, which has a voltage V, is going to be the same voltage as the voltage across capacitor 1, and it's going to be the same voltage as the voltage across capacitor 2. Okay. At that point, even though in some sense there was never any current flowing, because there's no way positive charges can jump across that gap from the left-hand side to the right-hand side unless the electric field between them was on the order of 3 million volts per meter. So let's say you had those things, for instance, those two plates, let's say you had them a millimeter apart instead of a whole meter apart. That would still require a voltage of 3,000 volts for air to become ionized enough. In other words, the dielectric constant of air is about 3 times 10 to the 6 volts per meter. So unless that voltage is that high, no current, no actual charge jumps from the left side to the right-hand side. But you would still measure a current if you broke the circuit and put in a multimeter running as an ammeter. Remember, for an ammeter, you actually have to break the circuit. It's got to be in series with the wire that you're actually measuring the current through. So you could detect a current while the charge is building up on the two capacitors, but it will stop once the voltage across capacitor 1, capacitor 2, and any number that are in parallel together, once that voltage turns out to be equal to the battery voltage. We also know that the capacitance formula is charge per unit voltage. So what we're ultimately trying to do here is we're going to try to find a equivalent capacitance such that this battery V behaves exactly the same way if you were to expose it or connect it to exactly one battery called C equivalent. And I'll put 2 parallel bars to remind us it's parallel. You can also write C equivalent sub P if you wanted. And that's really what we want to do, is how can I forget about there being 2 different capacitors? How can I replace the circuit with one capacitor and the battery not know the difference? Well, again, we see in this case, the total charge Q must be the exact same as the total charge Q in the left figure. So I wrote that down there. So what I know is if I take this equation that I'm calling, say, equation 1, if I take that and write it down using the C equation, which I'm calling equation 2, I see that Q is actually C times V. So 1 and 2 becomes C equivalent / parallel times V is equal to C1 times V1 plus C2 times V2. Does everybody see how I got that from equations 1 and 2? Now, because of equation 3, and because no one said they were confused by it, I can now divide out the C1, the V1, the V2, and the V, because they're identical. And we now have the true expression I was going for, which is C equivalent in parallel is equal to C1 plus C2 plus ... for any number of parallel capacitors. Now, if any of y'all are electronics technicians, say from past jobs or from the Navy or whatever, you might recognize that formula as looking like the formula for resistors in series. And that does turn out to be the case. The formula for resistors in series is exactly the same as the formula for capacitors in parallel, and vice versa. The formula for resistors in parallel is exactly the same as the formula for capacitance in series. So let me now explain what happens when you put capacitors in series. So I'm going to start off with black pen again. I don't know why I switched to red last time, but I did. So here we are. All right, so I'm going to have a battery, a pile, if you will. And the wire is going to run over here, and then it's going to go up over here, and then it's going to go right here. And right there is going to be a capacitance C1. And right there is going to be a capacitance C2. And let's get fancy, and I'm going to put a third up here. Ooh, a capacitance C3. Ooh, fancy, Mr. Younger. All right, so what's going to happen here is not unlike what happened before. The battery, which has a voltage V, of course, is going to be compelled to push a buttload of charges, say Q, which I meant to write in red, but I didn't. I'm going to do it again because I can. Okay. Now that charge Q is just because the potential energy and the electric potential is higher at the positive end of the battery. So in principle, that means positive charges would run away from it. We know in reality, it's actually electrons and they're going the opposite direction. But it turns out there's only one experiment you can do in which that makes a difference. And unless you're doing that experiment, it turns out you can always pretend like positive charges are leaving the positive side and entering the negative side. And so far, we haven't found a realm other than that one experiment, which is called the Hall effect, Hall. Other than that one experiment where you get bitten by doing that. So it's perfectly fine to pretend conventional current exists. Now, what's going to happen is notice capacitors are literally what they look like. They're basically a plate that's electrically isolated from another plate. In other words, either airs between them or they'll put something called a dielectric, which I made fun of myself last time by letting you know that I didn't realize till sometime after my course that the word dielectric is essentially the same thing as a just saying something's an insulator. Okay. So it's literally a metal that runs from the positive side of the battery, namely the wire, all the way up to the positive plate of C1. And that's essentially a metal. It's definitely a metal, and it's almost always, just aluminum or copper or something like that. Then there's an air gap or a dielectric gap. Then there's another piece of metal connected to another wire, connected to another piece of metal. That's the left side of C2. Then there's another piece of metal, the right side of C2, connected to a wire, connected to another piece of metal, which is the left side of C3, which again, across an air gap is another piece of metal, which is the right side of C3, and then a wire connected to the negative side of the battery that actually allows a charge Q to return back to the battery. Once all that has done such that V1 plus V2 plus V3 is equal to V, then the current will stop flowing. I'm going to call that equation 1. Okay, so what you'd see happen in this case is in fact a charge Q is going to appear on the left-hand side of this first capacitor C1. That's going to compel a charge of negative Q to appear on the left side, or excuse me, on the right side of C1. And because that's an isolated chunk of metal, that's going to force the right hand, or on the right hand side of C1, that's going to cause the left hand side of C2 to become exactly the same charge Q, positive on the left side and negative on the right. That's going to cause the same thing to happen to the left side of C3, which is going to cause the same thing to happen to the right side of C3. So in fact, what we see is that Q1 is equal to Q2 is equal to Q3, which happens to just be equal to Q, what the battery knew left it. Okay. Again, what we're shooting for here, and I'll write it in red this time, is the battery to be thinking nothing changed, even though I replaced those three capacitors with one capacitor C equivalent sub S for series. And that's what I'm trying to figure out. So this is equation 2 here. Q1 is equal to Q2 is equal to Q3 is equal to Q. And again, we have equation 3, which says that C is equal to Q over V, which you can actually use to find that V is equal to Q over C. Okay. So now combining equation 1 and 3, so equation 1 and equation 3 gives me the fact that Q1 over C1 plus Q2 over C2 plus Q3 over C3 is equal to Q over C equivalent series. Okay. So now you can see that I can apply equation 2, say apply 2, and now we're going to get, in fact, that C equivalent for series capacitor is 1 over C1 plus 1 over C2 plus 1 over C3 plus ... for however many capacitors you have in series. I should have actually outlined this one in red as well, but I did not. And because of my OCD-ness, I probably am not going to be able to live without erasing the blue line around this thing. So bear with my mental illness for just a brief period, if you don't mind. Okay. Oh, that was bothering me. Yeah, I'm sorry. It's a sickness, and I'm on medication, so I'm doing better, but still. Okay. So this is kind of neat. These two results, especially if you guys already know, like y'all been electronic technicians or something in the Navy or did it at some previous past life or whatever, you already know a little bit about what this formula means. The series formula is quite interesting in that what happens is no matter what capacitances C1, C2, and C3 are, when you put them in series, the total capacitance is going to be less than the smallest one in there. So if you add capacitance, say 2 microfarads, 3 microfarads, and 5 microfarads, the equivalent capacitance is going to be less than 2 microfarads. Whereas when the capacitors are in parallel, they just add like normal. So if you had 2 microfarads, 3 microfarads, and 5 microfarads, you'd end up having a total of 10 microfarads. So those are the two formulas. And like I said, it gives you a little insight into how capacitors behave when subjected to a voltage, say a battery. Does anybody have any questions about that? And let me turn on the chat again in case somebody's chatting me. Okay, I did. I'd already seen the John Mitchell post about the test, so I'm good on that. So any question, anyone? So let me show you, not that complicated, but something that looks a little complicated. I'm going to show you how to apply these formulas. And in this case, it's not going to be super hard, but it's not going to be super easy either. So my problem is going to be a single battery. Okay, that battery is in fact going to have a voltage equal to 12.0 volts. Okay, it's going to go up and run into a capacitor that is C1 and happens to be 4.0 microfarads, then that is going to break apart and make another parallel set of capacitances. This one's going to be C2 equals 3.0 microfarads. And down here, it's going to be in parallel with a capacitor C3 is equal to 5.0 microfarads. Notice I'm just trying to make sure each one has a different number so that you will not mistakenly think I was working with one capacitor rather than the other. Now, in addition to this holy mess, I actually also have a wire that comes around here and connects to another capacitor. And then this wire comes back and connects with this wire. And this capacitor right here is C4. And that has a capacitance of 6.0 microfarads. And then this wire just comes back willy-nilly like it didn't know anything happened. Okay. Now, some of you, like I said, if you happen to be people that are electronics technicians or whatever, you probably see something gaudy about that. And that's right. Just ignore it for now. That's more of a discovery process for them. I'm going to change where I wrote C1. I'm going to write C1 is equal to 4.0 microfarad because, to be honest with you, I'm not completely in control of my brain. Obviously, I have some OCD issues that are really, really a problem for me. But anyways, let me get rid of that. That makes me feel better. And let me get rid of this. That makes me feel better. And some alarm is going off right now for my Alexa, and I have no idea what. I'm sure it's your house is on fire. Please leave the premises, and I'm ignoring it. Okay, so this is a typical type of problem that your textbook will give you, and it can get a lot more complicated. I could put two capacitors in parallel after C2, and then they come back together before running into that wire. So that's another way I can soup it up and make it worse. But what I'm going to do with just this is I'm going to show you how to basically make a series of equivalent circuits until eventually you've reduced the circuit to a single capacitor of the appropriate capacitance. The way I go about attacking such problems is I look for the innermost simple situation that I can immediately solve. To me, the innermost simple situation is the C2 and the C3 that are parallel, and parallel actually works really nice with capacitors. So I'm going to say this is equivalent. Whoa. I'm going to say this is equivalent to, here's my 4.0 microfarad capacitor. The wire came off of that and went up to here. What I'm going to do is replace that now with a, let's say CE is equal to 8.0 microfarads. Okay, so basically what I just did was eliminated C2 and C3 and replaced it with the equivalent, which we learned was in parallel capacitors add. So 3 plus 5 is 8. You might not realize it, but that wire right here, that junction, that can actually be connected to this part right here. And you would see that C3 is in fact, C4 is in fact in parallel with C1 and C2. That was the part earlier that I said some of my technician people or people experienced with electronics probably already recognized. So we now see that this 8 microfarad capacitor is in parallel with this 6.0 microfarad capacitor, like such. Okay. And then I go back, of course, to the battery with this. That's why I don't need to draw anymore. Now what I see is I have an 8 microfarad capacitor in parallel with a 6 microfarad capacitor. And I think you all know that 6 plus 8 is 14. So now I have a 4.0 microfarad capacitor in series with a 14.0 microfarad capacitor, like such. And of course, these would just go back to the battery. Now, I know that 1 over 4.0 plus 1 over 14.0 is the same thing as if I multiply 14 by 2, I get 28. And if I multiply 4 by 7, I get 28. So I'm going to say this is 7.0 over 28.0. And that's actually an extra sig fig there, plus 2.0 over 14.0, which actually has the right number of sig figs. That's clearly 9.0 over 28.0. And remember, this is equal to 1 over C equivalent in series. So I can conclude that C equivalent in series, which is just the reciprocal of 9 over 28. So 28 divided by 9, I know that 9 goes into 27 3 times. I got 1 left over, so that's 1/9. 1/9 is 0.111. So the equivalent is 3.111. And in fact, 2 sig figs divided by 3 sig figs ultimately left me with just 2 sig figs. So these extra last 2 are in fact extra sig figs. In other words, they're not significant figures. So I've now done part A of the problem, which was find an equivalent capacitance. The equivalent capacitance of that entire circuit is 3.11 microfarads. So in fact, I could go back and draw that 12-volt battery like this. 12.0 volts is equal to V. And that is, as far as it's concerned, just in series with a single capacitor of 3.111 microfarads. So that literally is what it thinks is going on there. Because of that, I can realize that the amount of charge Q that's going to actually charge up this capacitor can be easily calculated, because the charge Q only has one place to go in the scenario. It's all got to go on the 3.11 farad capacitor. So in fact, the charge, this is part 2, where I'm going to try to determine basically what are the charges on each of the capacitor. So what I can immediately see is that this 3.11 is going to define Q to be basically, remember, C equals Q over V. So Q equals C times V. I'm going to say that's 3.111 microfarads times 12 point, oops. Let me do this where the place I have more room. So I'm going to switch to my eraser and say that Q, the charge that left the battery, is C times V. And by C, I mean Q equivalents for the series. So that's 3.111, where these two are not sig figs, microfarads times 12.0 volts. Notice what I do with the prefixes here. I don't actually have to convert it to farads, because what I can do is I can just leave the microfarads, which hopefully by now you know from all the stuff I've told you as well as my videos, that when you have something like 3.11 microfarads, the 3.11 is being multiplied by micro and by farad. So the micro really just means 10 to the -6, and then the farad is just like a unit. So anyways, I can just keep that on there. And when I multiply 12 times 3.11, I get 37.332. So in fact, the charge that leaves the battery is 37.332. And here's what I was talking about, keeping the prefix. That's going to be microcoulombs, because a farad times a volt is a coulomb, but I already had a factor of a micro in there. Now that was 2 sig figs multiplied by 3 sig figs. So in fact, that means these last 3 digits are non-significant. I'm going to keep them anyways. As I told you, it's better to keep extra sig figs. Now, what that also tells us is, by the nature of the circuit, the battery that we had, I'll go back to black again. We had a battery down here and it supplied a certain amount of charge Q, and all of that charge, because it didn't have anywhere else to go, all of that charge had to go on C1, which was 4.0 microfarads. And that meant the charge Q1 was equal to Q, which is equal to 37.332 microcoulombs. So now I already know the charge on Q1. In fact, I also know that basically we have the equivalent of a 8.0 microfarad capacitor in parallel with a 5.0 microfarad capacitor, like such. And then, excuse me, I used the wrong one. Let's get rid of that. The 8.0 microfarad covered the 3 and the 5. So this is supposed to be an 8 in parallel with a 6.0 microfarad capacitor. Okay. And that all, of course, would come back to the battery. Now, again, we're going to get 37.332 microfarads on that first capacitor, but that first capacitor is going to then cause 37.3 microfarads to go into that junction. So that's Q1, which is also just equal to Q. Now, what we know is there's going to be a Q here that's for C2. So I'll call that Q2. And then there's going to be a Q here, and that's for the one that goes into the 6 microfarad, which was the C4. So I'm going to call that Q4. And Q4 I don't know, and Q2 I don't know. But what I do know is that V2 has got to equal V4, which is what you're going to figure out after you've done the electric fields lab. The next lab is series and parallel circuits. And you're going to see that when circuits or when objects are in parallel, they have the same voltage. So what I know is 1, C equals Q over V, and 2, V2 and V4 have to be the same. And if you solve C equals QV for V, you see that V2 has got to equal Q2 over C2, and V4 has got to equal, oops, I used the wrong symbol. Let me erase that. It's supposed to be a lowercase. So that's supposed to be Q2, and Q4 over C4 is going to be equal to each other. Okay. So what I know is that 37.332 microfarads is equal to Q1 plus Q2, just by conservation of chart. Excuse me, that was supposed to be plus Q4. And I know that I can replace Q4 by solving, let's say, this equation, which I will call equation 1. Whoa, what just happened? I hit the wrong button. Let's call this equation 1. Okay, so by equation 1, I see that Q4 is in fact equal to C4 over C2 times Q2, which I also don't know, but I do know that C4 is in fact 6 and C2 is in fact 3. So this would be 6.0 microfarads. It really did not turn out well. 6.0 microfarads over 3.0 microfarads times Q2, which means literally it's just Q2 times 2. So now I can plug this in equation. Let's call this one equation 2. So plug in into 2. And now what I'm going to get is 37.332 microfarads is equal to, and why did I have, what's that supposed to be? Yeah, that was supposed to be Q2, not Q1, whatever I wrote there. Okay, so everybody noticed that I had written Q1 down here in equation 2. That was supposed to be Q2. Sorry about that. I don't know why I did it, but here it is. Now it's Q2. Okay, so that should be 4. Yeah, okay, so that should be Q4 in terms of Q2. So all I'm going to have from equation 2 is Q2. Ooh, wrong color. Is Q2 plus 2 times Q2, which equals, of course, 3Q2. Now, from this, we can tell that Q2 is just 37.333 or 332 divided by 3. So if I divide that number by 3, I'm getting 12.444. Actually, I'm feeling like I need to write that somewhere else because it's just gotten too cluttered in that little spot. So let me erase this and just say, okay, this means that Q2 is equal to 12.444 microfarads. And that's the decimal spot right there. So that's another answer. Q2 is going to be 12.444 microfarads. And then, of course, we now have not only Q1, which we decided was the same thing as Q. So I'm going to write that over here and say Q1, oops, should have been that blue. Q1 is equal to this quantity. And then Q2 is equal to that quantity. And what we know is Q4 from equation, from the equation we had before, Q4, why do I keep doing that, darn it? Q4 is equal to 2 times Q2. And of course, we found out Q2 was 12.44. So I'm going to say times 2, and that gives me 24.88. $24.88 microfarads is Q4. Using my red to highlight that, I now know the charges on C2 and C4. What I don't know is the charges on C3, but notice that C3 was in parallel with C2. So that means V2 and V3 are equal. That means that since V is equal to Q over C, that means that Q2 over C2 is equal to Q3 over C3. So finally, I can say and I'm going to skip the algebra here because I suspect you all know how to do it, but basically Q3 is going to be C3 divided by C2 and then times Q2. So I'm going to take C3, which was 5 microfarads, and I'm going to divide it by C2, which we know was 3 microfarads. That's 5/3, and I'm going to multiply that by Q2, which we found out Q2 was 12.444. And that gives me 20.74. Microfarads again. So that's our charges. Of course, that also gives us our voltages and all that kind of stuff. So what we got for C4 was, or for Q4 was like 24.8. What we got for Q2 was like 12.44. Notice that the capacitance C4 was twice as big as C2. And the concept behind this is to learn that for a given parallel setup of capacitors, the capacitor with the highest capacitance, one, gets the highest charge, but in fact, their ratios are the same. So the ratio of the charge that C4 got to C2, since they were actually in parallel with each other, even though I drew it to not look like that, that means that C4 should have twice as much charge as C2 because it has twice as much capacitance as C2. And lo and behold, you see that Q2 had about 12.4 and Q4 has about 24.8. So that's the big concept that we learned regarding capacitors in parallel. So we know that conservation of charge means that the charge going into a parallel setup has to add up for each of the legs. The Q1 plus Q2 plus Q3 plus however many legs you have has got to equal the total charge Q that came into it. And now we've managed to work out what all those capacitances are. Of course, we could also say, what's the voltage across each one of them? And that's another important consideration. So now that we have the charge, let's say, what are the voltages across each capacitor? That turned out bad. So that's something we can do as well. So what we have here is Q1 was 37.332. Microcoulombs. What that was Q1. Q2 was 24.888. Microcoulombs. Q3 was 20.74 microcoulombs. Again, those extra sig figs. And Q4 was 24.888. Ooh, excuse me. Oh, I looked before wrong. Q2 was 12.44. This is 12.88, 24.888 is correct. But this one, the Q2, I copied errantly. So the Q2 was 12.444. Again, those extra sig figs. Microcoulombs. We also know, by the way, that C2 was 3 microfarads, C1 was 4, C1 equals 4.0 microfarads, C2 was 3.0 microfarads, C3 was 5.0 microfarads. And finally, C4 was 6, if I remember correctly. Yes, 6.0 microfarads. So the way our circuit worked is we had a battery whose voltage was 12.0 volts. And it ran out like this to a capacitor C1. Now, if we use our little bubbles, so this is me again, imagining connecting the negative side of the battery to the COM port, and then the red I would poke and write a little bubble there. So if I put the black COM port on the voltage multimeter at the back end, the negative end of the battery, I would essentially get 0 volts like this. And right here, I would get 12.0 volts. And like I told you before, in reality, right here, I would get maybe 11.99994 or something. But we're just going to ignore that and say that should be about 12.0 volts right there. And actually, let me write that a little clearer. It turned out pretty crappy, actually. So say 12.0 volts. Okay, so the voltage across C1 is Q1, or excuse me, C1 is equal to Q1 over V1. That means V1 is equal to 37.333 microcoulombs divided by Q1 or C1, which was 4.0 microfarads. So 37.333 divided by 4 gives me 9.333. So V1 is equal to 9.333 volts. And that means right here, the voltage would be, in fact, 12 volts minus 9.33, which would be 2.667. Again, carrying extra sig figs, that would be the voltage right there. Now, the rest, remember, is essentially the same as this capacitor, which was C2, and this capacitor, which was C3, and this capacitor, which was C4, all in parallel. All in parallel like that. And then the rest came back here. What that means is C2, C3, and C4 all have the exact same voltages across it. So V2 is equal to V3 is equal to V4, which should be equal to 2.667, 67 volts. So that should be what it is, just based on the logic of how circuits work. But let's check. V2 has got to be equal to, of course, Q2 over C2. Well, Q2, we found out, was 12.44 microcoulombs over C2, which is 3.0 microfarads. So 12.444 divided by 3 gives me, whoa. Did I write that right? Q2 was 12.444 and C2, make sure I did that one right. C2 was 3. So 12.444 divided by 3 That's weird. Something different's happening. I must have made an arithmetic mistake somewhere. Okay. And in fact, when I did this earlier, the 2.66 I know is right. So I must have got something wrong in the calculation of the charges for the C2, the C3, and the C4. I don't know exactly what went wrong, but I can tell you, and this worried me a little bit when I was going through it, but what I found when I did this in class earlier, I'll just write this down. I did find in class that Q1. So this is when I did it in lecture for my face-to-face class. And I had already worked it once to prepare, but I got exactly the same thing for Q1, which was 37.33 micro coulombs. And that gave me that V1 was equal to 9.333 volts. So at this point, everything checks. That's exactly what I had. What I did get for Q2 though, what I got for Q2 was C2 times V2, which in other words, I used the 2.667 to do that. And when I got that, I got 8.0 microcoulombs. And Q3, I did the same thing using C3 V3. And in that case, I got 13.3 microcoulombs. And Q4, which was C4 times V4, and V, all those voltages I said were the same, but this one came out to be 16.0 microcoulombs. And I was happy with those numbers, but notice they're distinctly different from what I got. So I'm trying to figure out what went wrong. When I did C2, how did I get Q2? Well, let's see. It looks like I did C2 is equal to Q2 over V. That would be one way I could do it. But did I get Q2 right? Well, I got Q2 was 12.4. That does not mesh with my original C2. Does anybody have any questions or see anything jumping out at you that could point to why this is wrong? I can tell since I didn't get 2.667 for the voltages, I know I did something erroneous in finding Q2, Q3, and Q4. So if y'all see anything, let me know. What I said was Q2. Oh, I said Q2 and Q4 have to add up to give me the total Q. Oh, I think that's the problem. What I really had, where I'm showing that Q equals Q1, this area right here, what I really had there was actually 3 different legs, and each of them should have had the same voltage. I think what I've set up now is the 8 and the 6 have the same voltage, but possibly the 3 and the 5 wouldn't. So if I look at the voltage for C3 and C5, C3, I would get Q3. Let's try what that is. I would get Q3 over C3, so 20.74 divided by 5. Yeah, that gives me 4.18, which is entirely different from the voltage that I got across the other one. So I must have made a mistake somewhere in there. What I'll do is I will offer this. You guys can look for whatever error I made in finding Q2 and Q3 and Q4. So I'll write it right here. Extra credit. redo this problem and try to discover my error. I think tonight's results were wrong. But it could have been that my lecture results were erroneous. So don't assume anything in terms of which one's right or wrong. Just work it out, see what you get, and then you'll probably get one of the two I get. You might get a third. At that point, you might be able to look and see what I did wrong on the other one. We've only got about 6 minutes left. There's a problem I really want to show you guys, so let me try to do that real quickly. And this is not unlike a problem in your book. I'm just using entirely different numbers. Let's say we had a 100.0 volt battery that I connected to a, let's say this is a 10.0 microfarad capacitor. And this is a 25.0 microfarad capacitor. And they're in parallel with each other, and this battery charges them up. What I'm going to do is I'm going to let this battery charge them up. And my question is, what is, let's call this C1. Let's call this C2 equals. My question is, this gets a charge Q1 and this gets a charge Q2. I want to know what is Q1, what is Q2, and then I'm going to disconnect the battery and flip the resistors over, because what's going to happen, or the capacitors over, because what's going to happen is I'm going to get a certain number of charges on this one, and a certain number of charges on this one. But then when I flip them over, I'm going to connect a positive Q1 to a negative Q2. And therefore, a lot of cancellation will occur out, whatever the difference between the two is, I'm now going to have the sum of those two as the charges. And then I want to know what is the new charge, lowercase q1, lowercase q2, and new voltage. In other words, when we connect them, they're going to have an entirely different voltage than the 100 volts. So I've only got like 4 minutes to do this. So first off, let's realize that C equals Q over V. This is a solution. C equals Q over V means that Q is equal to CV. So Q1 is equal to 10.0 microfarads times 100.0 volts. That gives me a total of C of 3 sig figs. So I'm going to say Q1 right now is 1.00 milli coulombs, because basically 10 times 100 gives me 1,000. I had 1,000 micro. 1,000 micro is the same thing as a milli, so I got that. Now I'm going to say Q2 is equal to 25.0 microfarads times 100.0 volts. And that's going to give me Q2 is equal to 2500. So that's 2.50 times 10 to the third times micro. So that would be, again, a millicoulomb. So that's my charges now. Now, after which I'm going to reconnect them. So I've got 10.0 microfarads in parallel with a 25.0 microfarad C2, C1 like this. Now, what I know is this is going to have a charge Q1, this is going to have a charge Q2, and basically it's going to be plus, and this will be plus, minus, minus. And I want to know those. Well, what I do know is that, let's say Q2 minus Q1 has got to equal Q1 plus Q2. So Q2 minus Q1, you can see that that is 1.50 millicoulombs. So 1.50 times 10 to the negative third coulombs is equal to Q1 plus Q2. But I also know that V1 new is got to equal V2 new. And that, of course, means Q1 over C1 is equal to Q2 over C2. So I can say that Q2 is in fact equal to C2 over C1 times Q1. Well, the C2, of course, was 25 microcoulombs over 10.0 microcoulombs. Okay, so that's clearly 2.50 times Q1. So it's 2.50 Q1. So now I know that 1.50 millicoulombs is equal to Q1 plus 2.50 Q1, which means 1.50 millicoulombs is equal to 3.50 Q1. So I can finally say Q1 is equal to 1.5 divided by 3.5. And that gives me 0.4286, 0.4286 millicoulombs. That's one answer. And the other answer, of course, is going to be 2.5 times that. So Q2 so Q2, which equals 2.50 times Q1, has got to equal 1.071. Millicoulombs. Which is that charge. And of course, either one can give us what the new voltage is. V new is just going to be Q1 over C1, for instance. So I can say, actually, since I've got Q2 on my computer, on my calculator already. I'm just going to divide that by C2, and C2 was a 25 micro, and that gave me 0. Well, I need to write it better than that. That gave me V new equals, now I'm dividing Q, and what was it? It was Q2 was the one I did. So 20.5 milli over 2.5 micro, which gave me a kilo. So this is 0.429, 0.0429 kilovolts, which is actually equal to 42.9 volts. So that's the final answer. I'm sorry I had to rush through that one, but time's up now. Oh, actually, I went 3 minutes over anyways. Crap. Okay. Well, you guys are free to go. I'm waiting for the last person to leave in case anybody has any questions. But yes, there is a test available. Make sure you get that knocked out. You got till the 8th. I'm probably going to be putting test 2 up soon too, and you're probably not going to have a much longer wait than February 8th. It's going to be pretty soon thereafter. In other words, the test 2 will be due. So get your stuff in order and get cracking. Again, I'm waiting for the last person to leave in case anybody has any questions. Have a good evening.
Earlier when you were talking about something about emailing you the work, you were kind of breaking up, so that's all I really heard about that one.
Okay, gotcha. So what I was telling them is there's a typical problem there are 2 typical problems that I do in this course, and it's a multi-step, multi-length, multi-part problem where I'll say use Gauss's law or Coulomb's law to find the electric field of this. Okay. Hopefully for your sake, it's the Gauss's law one, because Gauss's law is so much easier than doing the integral form of Coulomb's law. Then I'll say, okay, now use the fact that the change in voltage, which is V final minus V initial, is equal to the negative integral of E dot dl, that path / line integral I told you about. Use that fact to determine the voltage difference between these 2 parts of that thing you just found the electric field for. Okay. Once you have that, part C would be, okay, use capacitance equals charge divided by voltage to compute the capacitance of that thing that you just calculated the electric field and the voltage for. That is a nice, robust, sort of what I call capstone problem of the first 4 or 5 chapters. I do a similar problem when we get to magnetism, but instead of using Coulomb or Gauss, we use Biot-Savart or Ampere. And then instead of finding voltage, we find flux, magnetic flux. And instead of finding capacitance, we find inductance, which is something measured in henries. Both of those types of problems are very key. And it's not unlike me, on a online test or a proctored test to actually have such a problem. And then in the problem, it'll say, note, do your work neatly. And immediately after the test, you have 15 minutes to take a photograph of this work and email it to me. So that's all you missed is there is occasionally a need where you'll have to do that. You'll take a photograph of the entire work, even if it's, front and back of 3 pages or whatever. You'll take a photograph of the entire work within 15, 20 minutes after you finish your test and email that to me. That way I can, see that you're actually able to do the problem, as well as I can give you partial credit in the event that you just made some careless mistake.
All right. That sounds awful for a time test, but
yeah, it's usually not that big a deal. And in fact, what I've been trying to do is show you Gauss's law so many times. That's one of the reasons I made so many more videos this semester for Gauss's law, so you get used to doing that. And when I do capacitance, I've done it now with a cylinder, and I've done it now with a parallel plate, I've gone through that process of Gauss's law, computing all that. So give that a try. Look at your notes in your book as well, or excuse me, the examples in your book that has good examples. There's mine are full lectures, but just choose the part of the lecture. A lot of them are full lectures. They're like an hour and 25 or an hour and 30 minutes, because some of them are summer classes, which are real long. But feel free to fast forward through it until you get to the part that you want, which is like a Gauss's law problem. Okay.
All right. I'm guessing we don't have to worry about that if we want to go for like another attempt.
What do you mean?
I'm pretty sure that the test, the test
Oh yeah,
has
you get
3
multiple
attempts.
attempts. Yeah, so when I do a test like that, that's one that appears every time. So it's not quite not quite so nice. And I usually, to be honest with you, I usually do it on the proctored test. So it's normally done on the midterm or the final. That's the most important time, and you only get one poke at that one.
All right.
So just the main thing I'm saying here is you definitely need to know how to use Gauss's law to compute electric field. Long as it has those certain symmetries, it can be done. The symmetries are, it's got to be an infinite plane, it's got to be an infinite or very long wire, or it's got to be a sphere. If it doesn't have those symmetries, essentially you cannot do it with Gauss's law. You're going to have to use Ampere, or you're going to have to use Coulomb's law. Okay.
All right.
All right. Let me know if you need any more help with that. You can always take a photograph of any of the problems you're trying to work, whether they be on a practice test or my lab and mastering homework or whatever. If you take a picture of that, and if it's multiple choice, take a picture of the answer choices too. Send that to me, and I can either help you via text, or I can call you, or FaceTime you, or set up a Zoom session, or sometimes I just solve the problem in general and post it on my YouTube channel, or I change it a little bit so I can post it on my YouTube channel. But let me know if you need anything else.
All right. Have a good weekend.
You too. See you, John. It is John, right?
Yeah.
Okay. See you, John. Have a good one.